Alrighty, so we're going to be doing turning points, 3, 4. Our I can statement you can see is we're going to just, I can name turning points. First off, a turning point is where a function changes. Go back to the pen I like. Let's actually go to a pen. Direction. Turning points are also known as local extrema. So, what do I mean by local extrema? If we draw a simple function right here, local extrema are, or these little bits where they change direction, where the slope is 0. We'll change color to highlight this. These points are the local extrema, or the turning points. It's when a graph or a function changes from going increasing to decreasing, or from decreasing to increasing.
Can you repeat that real quick?
Yeah. So turning points are where a function changes directions. They're also known as local extrema, and extrema means either a minimum or a maximum. So so this point here, if we think, I'm just going to label it point 1, it can't go the function no longer goes any higher than this point in this general area. So it is a local extrema or a local maximum. If we look at point 2, it is a local minimum, because in this general area, the function can still go lower than this. It's just in this area, it does not go any lower. It changes directions. It goes from the function goes from increasing to decreasing, or it goes from decreasing to increasing. You could also think of it as the slope is changing from positive to negative, or from negative to positive. So, scrolled way too much. When we think in terms of a function, or when we see a function, so a function with the degree, so our first one is a degree of 1. We all know x minus 1, if we were to graph that, it's just a line. It'll have 1, 0, or one point where it crosses the x-axis. But it has no local extrema, or it never changes direction because it's just a straight line. Never curves, never changes. When we have a polynomial with a degree of 2, we know that's our parabola. It has 2 zeros, and it changes direction once. As you know, that's our U shape. I'm going to fill out the rest of these. So we have 3 degree of 4 and a degree of 5. And you might have started to notice a pattern that the number of zeros is equivalent to the number of degree, or to the degree number. And if we think into our local extremas, it is 1 minus the degree number. So just to draw these out, this is a cubic. And we have our 4th degree polynomial, and then our 5th degree polynomial looks something like that. So they have this. So when we summarize what we see, the degree equals the number of zeros. And the number of extrema is 1 minus the degree. So now we're just going to fill out this graph of what to look for when you're asked for a certain thing. So when you're asked for zeros, you want to see that it crosses the x-axis. And your answer is going to be a point. Yeah, points are in the terms of usually in an xy. What function is positive, we want to know when it's above the x-axis. And that's going to be an interval of x's. And when negative, we want below the x-axis. And again, it's going to be an interval of x's. When we're looking for the end behavior, we did this yesterday. We're looking for what's it doing at the arrows, or where the arrows are headed. And that's either going to be a value on the y, or it's going to be an infinity, either negative or positive infinity. When we're looking for a function, if it's increasing, we're looking for a positive slope. I'm going to take space, so we're going to do a positive slope. If it's decreasing, we're looking for a negative slope. And that's also going to be, your answer is also going to look like an interval of x's. Meaning from like, if we're looking for the interval from this point to this point, we would only need to write down the x coordinate, or the x value. So if this is -3 and this is -1, our interval would look like -3, comma, -1. It looks like a point, but it's not considered a point. Ooh. And same thing for our negative slopes. So turning points are slash minimum slash maximum. So for minimum, we're looking for the bottom of a hill. Yeah. So the bottom of a hill. Meaning, I'm going to use red. Meaning this right here would be the bottom of a hill where two lines come together. And for maximum, we're looking for top of the hill. For minimum, it's more like a valley, the bottom of a valley, not a hill. So I'm actually going to change that because that makes more sense. Of a valley, if I knew how to spell. And these are also, your answer is going to look like a point for both of these. So we have a couple of examples to work through. First, we're going to want to graph it. Using the table of values, approximate the following characteristics, and then sketch the polynomial. I'm actually going to change to black. So at -3, we go up to 9. It's a little off the charts, but we're just going to write it there. At -2, we're at 0. At -1, we're at -2.5. At 0, we're at -1.5. I'm actually going to change this to make this a little more visible. At 1, we're at 0. At 2, we're at -1. And at 3, we're at -7.5. It's down here. Now, then we're just going to want to sketch this. Make sure to draw your arrows at the end so you can know what you're looking for your end behavior. And then we're just going to find it. So, what are our zeros? So we can find out by just looking at the chart. We have a 0 at -2, 0. And we have another 0 at 1, 0.
So what about the 0 at 0?
So that is not considered a 0. That is our y-intercept. So that's where it crosses the y-axis. When we talk about zeros, we talk about where it crosses the x-axis and where it crosses, and only the x-axis. So it crosses the x-axis at -2 and 1. So next we're going to talk about increasing, which we're just going to, come on, stop doing this. Okay, it wants to play it like this. Change the transparency just a little bit so we can highlight. So right here is where it's increasing. Dang it. And when you're looking for increasing and decreasing, you're always looking from left to right. So as you look from the left going towards the right, the graph, what is the graph doing? So let me put my colors back, or my sizes back. So it's increasing on the interval from, ooh, that's very right, from -1 to 1. Yes, yes, so these intervals are only the x values. So from the x equals -1 to x equals +1, the slope is positive or the function is increasing. Yes, except since it's a function, it continues on indefinitely. 1 to infinity would be our second interval. Our first interval would be on the left side. So we'd have -infinity to -1. And we would combine these two intervals by this little u symbol. Yes, so you'd want to write both of them, because that's the full part of the function. So the function decreases from -infinity, from x equals -infinity to x equals 1 to -1, increases when x is -1 to 1, and then it decreases when x is 1 to infinity. So then we're going to look at our turning points. I'm going to highlight our turning points are when we change direction, so it's going to be right in between our slope intervals. Anyone want to take a guess at one of our turning points? It's just stay the point. Yep. So it would be the -1, -2.5. You can use our chart to see that. Which, this is more of an approximation because we don't know the exact point. So it very well could be over there, depending on how if we actually graphed this function out. I'll show you that for the second problem, why this is just an approximation, but it's a close enough approximation that is the value we're going to work with. And then our other turning point. So the 0, -1.5 is actually, it's still along this increasing line. So our turning point is where it changes from, say, increasing to decreasing or decreasing to increasing. So our other turning point is this 1, 0. So then we want to know when the function is positive and negative. Just a reminder, positive is when it's above the x-axis. Negative is when it's below. So we can see that, and these are going to be ranges of x. So we know that the function goes off from -infinity, and it hits the x-axis at -2. And that's the only point in this function that is actually above the x-axis. And then, for our below the x-axis, we have the -2. And because it actually hits the x-axis here, it actually goes to 0, we can't include the 0. So it goes from -2 to 1, and then the little u combination, 1 to infinity. And the reason why we do that is because 0 is not either above or below the x-axis, so it's not negative or positive. And then we want to look at end behavior. That's when we come back to our limits. We have limit as x approaches infinity of f of x, and that equals, and the limit as x approaches negative infinity of f of x. Anybody want to shoot a guess as x approaches infinity? What is the function doing as x gets really, really big? That's the right side. It's getting smaller, which means it's heading towards negative infinity. And as we learned from yesterday, when we have a degree of 3, our end behavior is the opposite of each other. So that means the limit of as x approaches negative infinity, or we can see it in the graph, as x gets really, really small, or heads more left, the function gets really, really big. So with this one, we weren't given the function. Well, we were given the function, we weren't given the table. So what I've done is I've used Desmos to graph it for us so we can get these specific points out. So, let me go find this point. So when x equals -3, our function equals 40. Go to the right page. So we have 40. When x is -2, y is 0. When it's -1, it's also 0. When we have x equals 0, our y is 4. And to speed this up, it's actually symmetric along the y-axis. So those are our points. We're going to just throw these points up really high for the -3 and 3. At 0 it equals 4. At -1 we're at 0, and at -2 we're at 0. But we saw that when we actually graph this, it drops a little below, then it goes up, comes back down, a little below, and comes back up. So we'll have a graph that looks like that. So you can probably see we already have our zeros. They're at -2, 0, -1, 0, 1, 0, and 2, 0. Let me get the shading up again for when we do. So again, we're going to shade increasing in green, and we'll use blue again for decreasing. So it's increasing here and here. And then decreasing along this. So we're going to write our intervals. So it's increasing somewhere between -2 and -1. So we'll just call it -1.5. And it's increasing all the way up to when x equals 0. And we combine it. Similarly on this side, it changes to increasing somewhere between 1 and 2. We'll call it 1.5 again. And it increases like this until infinity. So similarly for decreasing, we're going to have 2 intervals. So starting on the left side, it is decreasing from negative infinity all the way to our little interval to negative 1.5, and then it decreases from 0 to 1.5. As you notice, the intervals are increasing or decreasing. If we put them together, we'd get the whole function. So it's decreasing, then it's increasing, then it's decreasing again, then it's increasing finally. So it's going from negative infinity all the way over to infinity. If we looked at them in order, did we ever? So we have a degree of 4. If we look back at our chart, we'll have 4 turning points. Scratch that. Looking back at our chart shows us that we should have 3 turning points, not 4. We would have 4 zeros, which we have. And then 1 minus that's the 3 turning points. Those turning points, we did in red, happen at these intersections. So they're going to happen at our negative 1.5. I don't actually know how far that goes down. We'll say it gets close enough to negative 2 that it's more we'll just approximate it to negative 2. Our other turning point is that 0, 4. And our last turning point is going to be at 1.5, 2. So 1 is the graph positive. The graph is positive from negative infinity to negative 2. And it is negative 1 all the way to positive 1. And then we need to combine it again so that we have from 2 to infinity. When is the graph negative? The graph is negative from negative 2 to negative 1, and from positive 1 to 2. Last but not least, we're looking at our end behavior. So the limit of x approaches negative infinity of f of x equals, and the limit of x approaching infinity of f of x equals. If you remember from yesterday, we have a 4 degree with a positive leading coefficient. So they both arrows are pointing up. So both of our end behavior is heading towards positive infinity. And we can see that in our graph. Both arrows are pointing up, heading towards infinity. So that's all we got for today.